Hi, I'm Alex Dickens from Team 2654E Echo, and this is our video on the command schedule we use in our code. This is the third video in our video series on programming, so let's get started. So first, going over the goal of this presentation, I want you to be able to describe how command-based programming works and why you'd want to use it. So I'll go into depth on how the command scheduler works, how you defined it, what is command-based programming, why I think it's useful, and then how you can use it in your own code, along with some tips and tricks at the end of the presentation for how I use it throughout this season. Okay, so going to some prerequisite knowledge. You're going to need to know how to work with classes and objects very well. I still recommend watching and understanding what I'm going to talk about in this video. However, if you really want to implement this yourself, you're going to have to have a very firm understanding of classes, objects, and inheritance. And then specifically for C++, the implementation detail, you're going to want to understand virtual functions. And for all of these things, Google them to find tutorials. I'm not going to be able to describe them as any tutorial on the internet can. So just take a look at those, Google them, understand them, practice with them, and then come back here and try and implement this yourself. Okay, going into command-based programming. Command-based programming is a design pattern for robot code. It allows programmers to focus more on what the robot does instead of exactly how the robot does it, with specific commands and implementation details for percentages and stuff like that. And before I go too in depth into this, I don't claim any of this work as my own. My implementation is very heavily inspired by WPILib. So take a look at their code if you ever want some more in-depth implementation stuff, and they have some excellent resources there. Okay, so there's many other options for like design patterns for robot code, of course, and there's these three here are probably the most common, I'd say. But I'm going to talk about what these are and why I think command based is better than these. First of all, finite state machine. This is some code from our robot last year. You can see we have, oops, you can see we have a state controller for the left wing and intake here, and we command those both individually. This worked very well last year when you had a lot of independent subsystems, and it it worked okay. But the thing is, when you have multiple subsystems working together and a lot of integrated commands that require multiple subsystems, it becomes much more difficult to work with this state machine architecture. Although its simplicity is helpful, it doesn't work well and scale well. And the same can be said about event-driven code. I don't have any examples here, but this is really when you use like the M events or micro events on the buttons on VEX code, or you think there's an alternative in prose. I never really experimented with this, but event-driven is what you say, when this button is pressed, do this, or when this limit switch is pressed, do this, and combining those together is what event-driven code does. And this is very good for simple things like making a back clamp toggle back and forth. But as you get to more complex projects with many different things interacting, such as like intake ejection systems or something like that, it becomes much more difficult to implement. And then finally, we have the sequential execution pattern. This is what most teams use for their autonomous routines. So you can see here we have this example one. It just has this drive forward command and then turn, shoot. It's where functions inside a function are run right after the other. It's pretty self-explanatory. If you're familiar with code, you've probably used this. Okay, so going into a code example, I'm going to describe some of my code from this year, how I implemented it with my intake subsystem, and then just how it made my code nice to use and stuff like that, why I think you should use it. All right, so now diving into the code a little deeper. Here I have the top intake subsystem. This is what we use to control the top intake on our robots throughout the season. And then going just a little bit into depth about this subsystem, it obviously owns a motor and an optical sensor, and this is used for the movement and the sensing on this section. Couple things to note about this function. No, there's no way that you can actually access the intake motor directly. You always go through these set percentage or something functions. This just allows that difference between the actual hardware of the motor and then how like the hardware works. So for this intake, really you only set a percentage, possibly a position. This is something that we did that was a little bit different than a lot of teams. But you either really set the position or a percentage. You don't really set a velocity or something like that. And that's just reflected in how this subsystem works. Additionally, you can see that there's a couple of functional commands and run commands down here. And you can see that in these commands, it just returns a new instance of the command that requires the subsystem and has a set percent function. Okay, so now digging into the subsystems, how like the sequences are made and how we go to the controller. You can see here that there's a bunch of sequences. Some things like this hang, an extremely complex motion is actually simplified into basically this much code. So it goes from here down to about here is all the code that's required for hang, which is really, really nice. You can tell that it's a lot simpler than it would have had to be if I had to write out exactly how all the subsystems work together, like how hangout worked every single time it happened, how to set the lift position and all that. All just doing it for me and then managing the lifetime of all these commands together was really helpful to design this code extremely quickly. And then another couple things, the top intake with eject, going back to that top intake subsystem, we have this percentage command until, and this command is actually really interesting. This whole thing, basically a one-liner, is able to do ejection without any other code. Basically, it intakes until it detects the wrong color ring at a certain position, and then once it detects that, it ejects it. So this is a really interesting piece of code because it majorly simplifies a very complex motion into a very small amount of code, and that is a lot of what I try and do is simplify everything I do to make it easy for me to make, and then also, which almost more important than making it initially, is maintain during the competition. And then one last thing to note is this primary.get trigger, or all these primary triggers here. This is the primary controller is basically saying when the driver presses button X, toggle this arcade on true or any of these other commands. And by chaining these together, you get to do some really powerful things in your code. Okay, so that's basically how the code works with command schedulers, basically the high-level overview of how this stuff works. Now I'm going to go back and talk about how this command scheduler is actually implemented. Okay, so now I'm going into the command scheduler implementation. First, I'm going to go over the abstract classes of the command and subsystem, and then go into how the command scheduler actually works. Now, starting with the subsystem, quickly I'm going to go over what this class really means. This is an abstract class to basically represent all subsystems that can be possible in a robot. What you'll use it for is you'll subclass it in your robot, such as when I do this bottom intake, I subclass the subsystem. And by doing this, I basically indicate that this, in any instance of this class, means that it's a subsystem, and I can use it later in the command scheduler to basically access multiple different command or different subsystems as if they're like the same object. That's what inheritance allows you to do, or polymorphism specifically. Okay, so now going into the command implementation. This command outlines a few commands. Initialize, execute, is finished, and end. So the initialize and is end, those are part of the life cycle I was talking about. So every time the command starts, it runs an initialize, and every time it ends, it runs an end. And by just looking at how those functions are run and then that interrupted Boolean there, you really get as like in each command, you can run a lot of advanced stuff. Okay. And then there's this is finished function. This function returns true if the command is finished. This is another part of that life cycle, but it returns false if it's still running. This function is used in the command scheduler to basically reschedule a command if one is finished. So then the most important function, arguably, of this command is this get requirements. So you can think of a command as requiring any number of requirements. So this is for parallels, it's requiring all the substances running at once. Or for something like a sequence, it's actually requiring all the commands it's running at once because it's very hard to change the requirements as you're going through. But by requiring all the subsystems that you're going to use, you're able to very effectively allocate the resources on the robot automatically without having to very explicitly tell it what you want it to do exactly. And then there's a couple functions down here. These just access the command scheduler, just makes it easier to interact with these commands, especially these Boolean ones, and then these and then with timeout and stuff like that. These just make it so you can like chain these commands together super easily. Okay. And then going to the command scheduler here, this is very similar to WPLA's command scheduler class. What it has is a list of subsystems. This is a subsystem unordered map of the subsystem and its default command. And then this subsystem and command are the requirements. So this is basically saying all the subsystems and if a command requires them, and then is requiring them currently, and this is all the subsystems and what they should be at default doing. This vector of commands is the scheduled commands. These are the commands that are currently running on the robot. Just going down here, we have these event loops. Teleop event loop just runs when the robot is in teleop, and then the event loop in general runs when other stuff is happening. Next is in run loop. This basically is an ad hoc mutex or something like that. It allows for the robot to understand when it's in the run loop, when sensitive stuff is happening with the scheduling and canceling of tasks very quickly. And by indicating that's in the run loop, you can add stuff to these to schedule and to cancel commands vectors that will do it immediately after everything is done. And then here's the automatic constructor. This is a private command that makes it so that this is a singleton class and it's only run once, and you have one collective command scheduler that you access at all times. And that's why all these functions are static. Okay, so moving on to this register subsystem, you have to run this at the beginning of your program, and you can see here, I run it right there. And what this does is basically says the subsystem and has this default command of tank. And I just do this for all the subsystems to make sure that they are like in an idle state at all times when no command is running on them. So you'll see that all these have this get instance. This is just that singleton pattern. It makes it very easy to use the command scheduler. You can see here that I don't have to actually do the get instance here, have a specific instance of the command scheduler. Since it's a singleton, it just runs once, and you have one specific command scheduler that you're accessing throughout all of your code. Next, going to schedule. This takes a command and then schedules it into the subsystem. You can see here that first it checks to make sure that they're not like it's already scheduled or something like that. And then it goes to the check if the current instance is in the run loop. And if it is, it puts it into the toSchedule command. And there's a couple other checks here, but basically then it just runs the command. It puts it into by putting it into isolating the requirements and canceling all commands that require that. And then by scheduling, adding it to the scheduled commands. Next, there's this function. This is a private function, or it's sort of public, but basically it's asking what the requiring command currently is of a subsystem. This is useful for some things in both in the private command scheduler, and then if you're trying to tell what command is running on a subsystem at a specific time, you can check it with this. Okay, so this run command here, this is what is run every frame, and it allows the command scheduler to update properly with all the things that have happened past 10 milliseconds with the is finished polling and then executing all the commands properly. It's first doing these periodic functions for all the subsystems, then the event loop, making sure that's up to date, and then it'll say that it's in this run loop. Then it runs all the commands execute function, checks if the command is finished, and then ends that command with interrupted equals false, and then it erases the requirements. The next step is to cancel the commands that need to be canceled and schedule all the commands that need to be scheduled. And then after that's done, it checks to make sure that all instances have their own subsystem. And if it doesn't have it, then it'll schedule the default command. Next, going to the scheduled function, it basically just checks to see if the command is in the scheduled commands list. It's very useful internally, and then also to check if a command is running in the subsystem. And then finally, this cancel command, this basically erases the requirements and the command from the subsystem, and it ends it, which is end command will tell it that it's done while telling it that it was properly interrupted. And then finally, it'll erase the requirements. And this may seem a little backwards, as like your code obviously didn't know and like reschedule stuff. But how this loop does every 10 milliseconds, it'll basically instantly reschedule a command or the default command when the next opportunity arises. And that's pretty much it for the command scheduler. You can see that these command schedule functions that are defined here are then defined, and it's pretty much it. I'm going to go quickly into one of the command compositions so you understand how that works, but all the command compositions are pretty easy to get the grasp of if you just read over their code. Just for simplicity, I'll go over this repeat command. Basically, what this command does is it just runs the same command over and over again. And if it's finished, it ends it and then reinitializes it. Basically, what this allows you to do is something like the eject subsystem or the eject function. It would make sure that the command is always running properly, and it'll restart it if it's stopped. You can see how it works here with the requirements and the end. Another interesting note is with these requirements in this parallel race group, the requirements are all the subsystems, so it makes a map of all the subsystems if it's not in there, so it's more like a hash set than a vector in this case. So yeah, that's pretty much how the command scheduler works. I hope you understand at least overall how this command scheduler works with all the commands and make sure that they're scheduled properly. And then we'll move on to how you should implement your commands and the best practices for implementing commands and subsystems in your own code. Okay, so now going into the robot implementation of the command scheduler. First, I'll talk about the subsystems. To really discuss the subsystem, you have to understand how the subsystem owns hardware. So you'll see here in this graph here of our world's robot that none of the, or not quite our world's robot, our state's robot, none of the subsystems own duplicate stuff. So like the top intake motor is only in the top intake subsystem. The Lady Brown subsystem owns the Lady Brown motor, which is only owned by the Lady Brown subsystem. and that's very important. It splits the robot into these very distinct subsystems that are entirely separate from each other. And this allows you for you to treat like basically the robot as data in your code, and then have the command scheduler work for you then and do almost everything that's like hard about scheduling these commands back and forth for you. Next, for commands, each command must require all the subsystems that are used. If it doesn't require all the subsystems that are used, you're going to run into a lot of issues. And I don't even mean to underestimate that. Like, you're going to have code running on the same subsystem, you're going to have a lot of issues. It just must require all the subsystems that it could use, and must like have that as a guarantee. Like, this requirements list must be correct. So if you're running into a bug, it's honestly probably you forgot a requirement somewhere. So commands will have a periodic method run under every 100th of a second by the command scheduler. Write stuff like PID loops in there, and then possibly setting the percentage of the motor. You can also do that in initialize to have it run once. And then commands can also indicate if they want to be done early. So use this for a lot of things where like, let me think of one, where like the path, when they're at the end of the path, it'll just indicate that it's done, but it might also have to be canceled early with like the until or wait wait timeouts. So, and then another thing to keep in mind is each command has a lifecycle with its initialize and end functions when it started and finished. Just use this very intelligently with your code. Maybe you have something that pushes a piston out, but it needs to make sure that it's in after the command is done. You can use it with the lifecycle there. And then an important thing to note is that the command scheduler's job is to ensure that commands always have resources available to it. So really take advantage of that. If you're like trying to make something work and it really just like needs some specific commands, or some specific hardware, just use the command scheduler, use that to your advantage, and it'll automatically figure out how that needs to happen. And then compositions are provided by the command API. They put multiple things together. Use these very smart. I mean, the sequence and parallel and race, if you use those smart together, you can do some pretty crazy stuff, like all the ejection sequence, all the hang stuff. There's basically no like code that I wrote in there, if that makes sense. It's all those sequences and parallels just grouped together with the until and other command compositions. And for organization notes, as I said before, make sure that each subsystem only owns its hardware and owns all of its hardware. If it'll make sure your stuff isn't being used twice and hardware is never duplicated. If you need to transfer data, consider using Lambda functions or something similar and setting that up in your code. In subsystems, I'd make it so that it's easy to access commands I use often, like the percentage command that I was talking about before. That just makes your code so much simpler with those like functional and repeat commands, something like that. It just really simplifies the work that you think about in your head. And then use command composition that I was saying previously. Don't make like ad hoc state machines in your code or like periodic loop. Just take advantage of the full features of command scheduler. Try and do some intelligent design. If something feels too complicated, take a step back and say, is this really the best way to do it? And just try it again real quick. It usually figures itself out after like 2 or 3 tries. And then finally, all my source code is public on GitHub. The documentation is at this link, command.alex.diggins.net. And then I have my example code base from this year. And this is all linked in the description. Additionally, if you want to contact me, that information is in the description. If you have any questions, please put them in the comments. Or if you have any bug fixes or something like that, you could just put those on issues in the repository. But make sure to ping me. I'll take a look at that. And thanks for watching.